Welcome to Y-Hub, the center of your curiosities. What if I told you that the Big Bang might not have been the beginning of everything? Imagine that our universe wasn't born from nothing, but from something even greater. A new study suggests we might be living inside a black hole formed in another universe. A universe inside a universe. But what does this actually mean? And what would it imply for our understanding of the cosmos? And, most importantly, can we figure out if this model really describes our reality? Let's try to make sense of it. In the standard model of the universe, everything began from a hot, dense phase we usually call the Big Bang. Although that term is misleading because it wasn't really an explosion. In reality, there was no giant bang at the start. Rather, there was an extremely rapid and violent expansion from a state of extremely high energy. This standard model, also called the Big Bang model, describes very well the evolution of the universe over the last 13.8 billion years. But it's not without its issues. It has some dark spots we still don't fully understand. Perhaps the biggest problem is that we can't fully describe what happened right at the origin of the universe. As we look further back in time, the density of matter and energy grows higher and higher until we hit infinite values of density, energy, and temperature. What physicists call a singularity. According to a famous theorem by Penrose and Hawking, this initial singularity would be unavoidable. And if this singularity truly existed at the beginning of everything, then space and time themselves wouldn't exist before it. There would be no way to apply the ordinary laws of physics because they simply wouldn't hold. The problem, however, is that this theorem only accounts for one of the two great theories modern physics uses to describe reality, Albert Einstein's general relativity. When we try to include the other great pillar of modern physics, quantum mechanics, things stop working smoothly. It gets more complicated, we don't know exactly how to treat the problem, and the initial singularity becomes far less inevitable than it seemed. In fact, it's entirely possible that the initial singularity never existed at all. In a new study published recently, some physicists approached the problem of the universe's origin from a radically different perspective. They hypothesized that the origin of our universe is actually linked to a gravitational collapse, the contraction of a huge amount of matter that led to the formation of a gigantic black hole. Unlike what the Penrose-Hawking theorem predicts, this contraction, this gravitational collapse, would not have produced a singularity. Instead, at a certain point, it would have turned into a bounce. The interesting thing is that from inside the black hole, this bounce would look exactly like an expanding universe. A universe just like ours. From the outside, however, it would simply appear as an enormous black hole, with a mass and radius comparable to those of our observable universe. In short, according to this model, which the authors call the black hole universe, our universe exists inside a black hole. This gigantic black hole would have formed within an even larger parent universe. The study doesn't provide a complete description of this hypothetical parent universe, nor does it say anything about its prior state. It simply assumes that the right conditions existed for a sufficient amount of matter to collapse in such a way as to form this enormous black hole and trigger, inside it, this bounce that would appear as an expanding universe. So in this picture, the origin of our universe isn't the beginning of everything, but rather the continuation of a sort of cosmic cycle. This idea, by the way, isn't entirely new. On this channel in the past, I've talked, for example, about physicist Lee Smolin's hypothesis of a kind of cosmic natural selection, in which black holes generate new universes inside them, as well as cyclic models proposed by none other than Roger Penrose himself, where a previous collapse gives birth to our universe. So it's not a completely new scenario, but the mechanisms used in this model are new. How can a gravitational collapse in a parent universe avoid producing a singularity, an infinite density, as predicted by the Penrose-Hawking theorem? How can it instead produce a bounce that gave rise to our universe? According to the authors of the study, we have to call on quantum mechanics. The key lies in what's called the exclusion principle, or Pauli exclusion principle. This principle states that identical particles, called fermions, cannot occupy the same quantum state. No need to get into too much detail, but the crucial point is that this study shows that the exclusion principle would prevent matter from ever reaching infinite density. As matter contracts and compresses, it reaches an extremely high, but finite, density, which changes its behavior and turns the collapse into a bounce. However, this bounce happens entirely within the black hole's event horizon. And, according to the study's authors, the bounce is not only possible, but, under the right conditions, would actually be inevitable. And here's another interesting point. All of this happens entirely within the framework of the two great theories I mentioned earlier, general relativity and quantum mechanics, the most successful physical theories we have. So, the model doesn't introduce any new elements, no new physics, no exotic matter or energy models. It explains everything with the ingredients we already know, ones that are part of established physics. And what emerges on the other side of this bounce, inside this black hole, is a universe surprisingly similar to ours. But there's something even more surprising. According to the black hole universe model, the bounce naturally produces two accelerated phases in cosmic evolution. The first is called cosmic inflation. It happens in the very first instance of the universe's life. The second happens much more recently. In the standard cosmological model, both phases lack a clear explanation and require additional components. Cosmic inflation needs a new fundamental field, the inflaton, which we haven't yet identified. The later phase of accelerated expansion, which the universe is still undergoing today, requires a mysterious component called dark energy, which fills all of space. In the black hole universe model, however, neither phase requires extra components. They would both be explained simply by the physics of the bounce. Even more interestingly, according to the study's authors, the value of the dark energy we observe in our universe would actually be related to the mass of the black hole, which is the total mass of our universe. This would elegantly explain why the dark energy we observe is small, but not exactly zero, something our current physics doesn't explain. So, without a doubt, the black hole universe model is a fascinating one. It describes our universe well, and even clarifies some mysteries of the standard model. But models, no matter how intriguing, must always be tested against reality. And in this regard, the black hole universe makes a quantitative prediction that could, in principle, be tested. According to the black hole universe, the geometry of our universe should have a slightly positive curvature. What does that mean? Using a two-dimensional analogy, it means our universe's space, inside this black hole, should resemble the surface of a sphere. Of course, we live in three-dimensional space, so this is just a visual analogy. We can't actually visualize the curvature of a three-dimensional space. For now, our observations don't show strong evidence of such curvature. And the reason might simply be that the curvature is so small, it's hard to detect. Much like how Earth seems flat to us, not because it is, but because the region we can see is small compared to Earth's full size. If the same is true for our universe, increasingly precise future observations might reveal hints of this positive curvature, and provide support for the black hole universe model. In fact, some recent observations do seem to point in that direction, showing small clues, small bits of evidence, that the universe might indeed have positive curvature. But it's far too early to draw definitive conclusions. The key takeaway is that the origin of our universe is still shrouded in mystery, and we don't know as much as we might think. Our universe could simply be something that exists within an even larger framework, and its apparent origin could arise from a pre-existing state. But for now, the black hole universe remains only a hypothesis, an extremely fascinating one, with certain points that make it very compelling, and one that makes predictions which, in the future, could be tested to help us better understand how things truly are. Share your thoughts about this model in the comments. If you enjoyed this video, leave a like. And most importantly, subscribe to the channel if you haven't yet, and turn on notifications so you'll always know when new videos are out.